The Multiverse Theory. The multiverse theory isn't a single idea, but a collection of hypotheses, suggesting that our universe is just one of many, perhaps an infinite number coexisting realities. This concept, once relegated to science fiction, has gained traction in theoretical physics as a potential consequence of our current understanding of quantum mechanics and cosmology. It forces us to confront the possibility that everything we know, every star, galaxy, and law of nature, might be just one bubble in a vast cosmic ocean of other worlds. The two most popular scientific origins for the multiverse are rooted in quantum mechanics and cosmology. The quantum multiverse. This idea stems from the bizarre rules of the quantum world. At the subatomic level, particles can exist in a superposition of multiple states at once. It's only when we measure a particle that it chooses a single state. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radical explanation. The particle doesn't choose at all. Instead, reality itself splits. For every possible outcome of a quantum event, a parallel universe branches off where that outcome becomes reality. In one universe, the particle is here. In another, it's there. Following this logic, every quantum event that has ever occurred, from the decay of an atom to the firing of a neuron in your brain, has created a cascade of new universes. This means there's a near infinite number of parallel worlds, including some where you made different choices and are living a completely different life. The cosmological multiverse. This version comes from the theory of cosmic inflation, our best explanation for the universe's rapid expansion just after the Big Bang. The theory of eternal inflation suggests that this inflation never completely stopped. While it ended in our patch of space, allowing our universe to form, it continues in other regions, constantly and eternally spawning new bubble universes. Each of these bubbles could cool and expand to become a universe in its own right, potentially with different fundamental constants and laws of physics. Some might be similar to ours, while others could be utterly alien and inhospitable to light. The primary controversy surrounding the multiverse is its testability. Science relies on hypotheses that can be proven false. Since we can't observe or interact with other universes, many critics argue that the multiverse isn't science at all, but rather a form of metaphysics or philosophy. String theory. String theory is one of the most ambitious and elegant ideas in modern physics. Yet it's also one of the most controversial. At its core, it proposes a radical reimagining of reality's fundamental building blocks. Instead of viewing particles like electrons and photons as zero-dimensional points, string theory suggests they are actually tiny, one-dimensional vibrating strings of energy. Imagine the string of a violin. By vibrating it in different ways, you can produce a wide range of distinct musical notes. String theory posits that the universe works in a similar way. Each fundamental particle is simply a different note, or vibrational mode of these underlying strings. An electron is a string vibrating in one pattern. A photon is a string vibrating in another, and a quark is a string vibrating in yet another. This simple, powerful idea is the source of the theory's elegance. It could potentially explain the entire zoo of particles we see in nature as different harmonies of a single fundamental entity. The greatest promise of string theory is its potential to be a theory of everything. Physics currently relies on two incredibly successful but mutually incompatible theories: general relativity, which describes gravity and the large-scale structure of the cosmos, and the standard model of particle physics, which describes the other three forces, electromagnetism, strong nuclear, and weak nuclear, that govern the subatomic world. When physicists try to combine these two theories, for example to describe the center of a black hole or the moment of the Big Bang, the math breaks down, producing nonsensical infinite results. String theory miraculously resolves this conflict. The way strings interact naturally includes a description of the graviton, the hypothetical particle that carries the force of gravity, thereby unifying all four fundamental forces under a single mathematical framework. However, this elegance comes at a steep price, leading to the theory's major controversies. Extra dimensions. The mathematics of string theory doesn't work in our familiar four dimensions, three of space and one of time. It requires the existence of at least 10 or 11 dimensions. To explain why we don't see these extra dimensions, theorists propose they are compactified, curled up into a tiny complex shape at every point in our space, far too small to be detected. Lack of experimental proof. This is the biggest criticism. For a theory to be considered scientific, it must make testable prediction. The energy levels required to see these tiny strings or probe the extra dimensions are trillions of times greater than what our most powerful particle accelerators, like the Large Hadron Collider at Cern, can achieve. With no foreseeable way to experimentally verify or falsify it, critics argue string theory has strayed from physics into the realm of pure mathematics. The landscape problem. Instead of producing a single, unique description of our universe, string theory appears to allow for a colossal number of possible solutions, perhaps 10 or more. Each solution would describe a different universe with its own set of physical laws. Loop quantum gravity. Loop quantum gravity is a leading competitor to string theory in the quest for a theory of everything. While it also aims to unite Einstein's theory of general relativity with quantum mechanics, it takes a fundamentally different and in some ways more conservative approach. Instead of postulating new entities like extra dimensions and vibrating strings, LQG attempts to quantize space-time itself. The core idea of LQG is that the fabric of space is not a smooth, continuous background as we perceive it. Instead, it's made of discrete, indivisible chunks or atoms of space. Imagine a t-shirt. From a distance, it looks like a smooth, continuous surface. But up close, you see it's woven from individual threads or loops. LQG proposes that space itself is like this. At the smallest possible scale, the Planck scale, space is a granular network of finite loops. You can't zoom in any further. This is the fundamental resolution of reality. This network of interconnected loops is called a spin network, and its evolution over time is called a spin foam. This granular structure of space-time has profound implications. Eliminating singularities. In general relativity, the Big Bang begins from a singularity, a point of infinite density and temperature where the laws of physics break down. Similarly, the center of a black hole is also a singularity. In LQG, singularities cannot exist. Because space is made of indivisible units, you can't crush matter down to an infinitely small point. Instead of a Big Bang, LQG suggests a big bounce. The theory posits that our universe may have arisen from the collapse of a previous universe, which, upon reaching the maximum possible density allowed by the quantum structure of space, bounced back to create the expanding universe we see today. No extra dimensions required. Unlike string theory, LQG is formulated in the familiar 4 dimensions. 3 of space and 1 of time. It doesn't require the existence of unseen higher dimensions, which many physicists find to be a more grounded and less speculative starting point. It focuses solely on merging the known principles of quantum mechanics and relativity without adding new unobserved elements. The primary controversy and challenge for loop quantum gravity lie in its difficulty in bridging the gap between the microscopic quantum world and the macroscopic universe we observe. While it provides a compelling picture of quantum spacetime at the Planck scale, it has struggled to show how Einstein's theory of general relativity, which describes a smooth spacetime, naturally emerges from this granular framework at larger scales. This is known as the problem of the classical limit. Furthermore, like string theory, LQG suffers from a lack of experimental evidence. The Planck scale is so small that directly observing these atoms of space is far beyond our current technological capabilities. While some physicists have proposed that LQG might leave faint, observable imprints on the cosmic microwave background, the afterglow of the Big Bang, or affect the travel time of high-energy photons from distant cosmic events, no definitive proof has been found. This leaves LQG, much like its rival, in a theoretical limbo, a mathematically beautiful and logically consistent framework for unifying physics, but one that remains unverified by the ultimate arbiter of science, experimental data. The simulation hypothesis. The simulation hypothesis proposes that our entire reality, the Earth, the stars, your consciousness, and your memories, is not a base-level physical world, but an incredibly sophisticated computer simulation. In this view, we are akin to characters in an advanced video game, unaware that our universe is constructed from code and information running on a powerful computational system created by a more advanced intelligence. This idea isn't new, with roots in philosophy from Plato's allegory of the cave to Descartes' evil demon. However, the modern argument was most famously articulated by philosopher Nick Bostrom. His simulation argument doesn't claim we are in a simulation, but that at least one of the following three propositions is almost certainly true. Civilizations go extinct. Almost all civilizations at our stage of technological development go extinct before they can develop the capacity to create ancestor simulations of their past. Civilizations lose interest. Advanced civilizations that do reach this capacity lose interest in running such simulations. We are almost certainly in a simulation. If the first two propositions are false, then an enormous number of ancestor simulations would be created by advanced civilizations. In that case, the number of simulated consciousnesses, like us, would vastly outnumber the non-simulated ones, making it statistically probable that we are among the simulated. The argument is compelling because of the exponential growth of computing power. We've gone from simple pixelated games like Pong to creating vast, photorealistic virtual worlds in just a few decades. If this trend continues, it seems plausible that a future or alien civilization could create a simulation of a universe with conscious beings that are indistinguishable from reality. Proponents of the theory point to several features of our universe that are strangely similar to a computed system. The universe is mathematical. The laws of physics can be described by elegant mathematical equations. The universe seems to operate on a set of rules, much like a computer program. A pixelated reality. At the smallest level, quantum mechanics suggests that reality is granular and not continuous. The Planck length, the smallest distance possible, could be seen as the pixel size or resolution of our simulated universe. The speed of light. The existence of a universal speed limit. The speed of light is analogous to the processing speed limit of a computer. It could be the maximum rate at which the simulation's processor can render the universe. The controversy surrounding the simulation hypothesis is multifaceted. For many scientists, it's an untestable and therefore unscientific proposition. How could we ever design an experiment to prove we're inside a simulation when the simulators could simply alter the rules to hide their existence? It's considered unfalsifiable. Any glitch in the matrix we might find could just be an unknown law of physics, and any lack of a glitch could mean the simulation is simply perfect. Furthermore, there are strong philosophical objections. The theory requires us to make assumptions about the motivations and capabilities of these hypothetical advanced civilizations. It also raises profound questions about the nature of consciousness, free will, and the meaning of life. If our reality is a program, are our choices real? Do our lives have any intrinsic value, or are we just data points in someone else's experiment? Despite these criticisms, the hypothesis remains a fascinating thought experiment that forces us to question the fundamental nature of reality and our place within it. Steady state versus Big Bang. The debate between the steady state theory and the Big Bang theory was one of the 20th century's most significant scientific battles. The steady state theory, popularized in 1948 by astronomers Fred Hoyle, Thomas Gold, and Hermann Bondi, was built on the perfect cosmological principle. This principle asserts that the universe is not only homogeneous, the same everywhere, and isotropic, the same in every direction, but it's also unchanging in time. As the universe expanded, a fact established by Edwin Hubble in the 1920s, the steady-state theory proposed that new matter was continuously and spontaneously created in the voids between galaxies. This new matter would then form new stars and galaxies, ensuring that the overall density and appearance of the universe remained constant for all eternity. To its proponents, this was an elegant, simple idea. The universe had no beginning and no end. It simply. In the opposing corner was the Big Bang theory, an idea that grew from Einstein's general relativity. Proposed initially by Georges Lemaitre, a Belgian priest and physicist. This theory suggested the universe was not eternal but had a finite origin. It posited that the universe began in an incredibly hot, dense state and has been expanding and cooling ever since. This implies a dynamic, evolving cosmos with a history. The name Big Bang was actually coined by Fred Hoyle on a BBC radio show as a term of derision to mock what he saw as an unscientific and absurdly creationist-like idea. For decades, the two theories competed for dominance. The debate was fierce and often personal, pitting two fundamentally different philosophical views against each other. The steady-state model represented an eternal, unchanging universe, while the Big Bang suggested a universe with a birth and a timeline, which some found uncomfortably close to religious creation myths. The turning point came in 1965 with an accidental discovery by two radio astronomers, Arno Penzias and Robert Wilson. While working with a large radio antenna in New Jersey, they detected a persistent, faint and uniform microwave noise coming from every direction in the sky. They couldn't eliminate it, no matter where they pointed their antenna. This mysterious signal was soon identified as the cosmic microwave background radiation. The CMB was a stunning confirmation of the Big Bang model. It was the predicted afterglow of the initial hot, dense state of the universe. The leftover heat from creation now cooled and stretched to microwave wavelengths by billions of years of cosmic expansion. The steady-state theory had no natural explanation for this uniform, background radiation. The CMB was a fossil from the universe's infancy, direct evidence that the universe had indeed been hotter and denser in the past. This discovery effectively ended the debate. The controversy surrounding climate change is unique on this list because the debate isn't happening among climate scientists. It's happening in the political arena, in the media, and online. Within the global scientific community, the conclusion is unequivocal. The Earth's climate is warming at an unprecedented rate, and human activities are the primary driver. Yet a significant gap persists between this overwhelming consensus and public perception, creating a controversy fueled more by politics and ideology than by scientific disagreement. The scientific consensus is built on multiple independent lines of evidence from geology, oceanography, atmospheric science, and biology. The foundational mechanism is the greenhouse effect, a natural process where gases like carbon dioxide trap heat in the atmosphere, keeping our planet warm enough for life. However, since the Industrial Revolution, human activities, primarily the burning of fossil fuels like coal, oil, and gas, have pumped enormous amounts of extra CO2 into the atmosphere. The data is unambiguous. The Keeling curve, a continuous record of atmospheric CO2 since 1958, shows a relentless upward climb from 315 parts per million to over 420 ppm today, a level not seen in at least 800,000 years. Global temperature records from agencies like NASA and NOAA show a clear warming trend, with the last 2 decades being the hottest on record. Physical evidence includes the rapid melting of Arctic sea ice and glaciers worldwide, rising sea levels due to thermal expansion and ice melt, and the increasing frequency and intensity of extreme weather events like heat waves, droughts, and heavy rainfall. This vast body of evidence has led more than 97% of actively publishing climate scientists to agree on the reality of human-caused climate change. This consensus is as strong as the consensus that smoking causes cancer or that the Earth orbits the Sun. So, why the controversy? The denial or skepticism doesn't typically come from peer-reviewed scientific research, but from a coordinated effort to sow doubt. The arguments often employ a handful of recurring myths. The climate has always changed. This is true. The Earth has undergone natural cycles of warming and cooling. However, paleoclimatology, which is the study of past climates, shows that the current rate of CO2 increase and temperature rise is happening hundreds of times faster than most natural changes. And it directly correlates with the spike in human emissions. It's the Sun. While the Sun is the primary driver of Earth's climate, satellite data since the 1970s shows no net increase in solar radiation. In fact, there has been a slight cooling trend in solar output, while global temperatures have continued to rise sharply. Climate models are unreliable. Models are projections, not crystal balls, but they are based on the fundamental laws of physics and have successfully predicted the general trend of global warming for decades. Furthermore, the consensus isn't based on models alone, but on direct, real-world observations. The roots of this manufactured debate are largely political and economic. The immense profitability of the fossil fuel industry has led to decades of well-funded lobbying and public relations campaigns designed to protect their interests by creating doubt about the science. This strategy mirrors the one used by the tobacco industry to deny the link between smoking and cancer. The issue has also become deeply polarized, entangled with political ideologies that oppose government regulation and international cooperation, framing climate action as a threat to economic freedom rather than a response to a physical reality. The result is a controversy where overwhelming data is pitted against deeply entrenched belief systems and powerful vested interests. Evolution versus intelligent design. The conflict between evolution and intelligent design is a classic battle between a cornerstone of modern science and a belief system rooted in faith. While the scientific community considers evolution by natural selection to be a fact, the fundamental organizing principle of all biology, ID presents a challenge based on purported evidence of a designer. This has created one of the most persistent and socially charged controversies, particularly in the United States, where it has played out in classrooms, courtrooms, and public discourse. Evolution by natural selection, as proposed by Charles Darwin, is a remarkably simple, yet powerful mechanism. It rests on three observable facts. Variation. Individuals within a population vary in their traits, which are size, color, sleed, etc. Inheritance. These traits are passed down from parents to offspring. Selection. In a given environment, some traits are more advantageous for survival and reproduction than others. Over generations, individuals with these advantageous traits are more likely to survive and pass them on, causing the traits to become more common in the population. This process, repeated over millions of years, can lead to the formation of new species. The evidence for evolution is vast and comes from many fields. The fossil record shows clear transitions of species over time. Comparative anatomy reveals shared structures, and modern genetics allows us to see the precise DNA similarities that link all life back to a common ancestor. Intelligent design, in contrast, is the assertion that certain features of the universe and of living things are best explained by an intelligent cause, not an undirected process such as natural selection. ID's central argument is the concept of irreducible complexity, famously illustrated with the example of a mousetrap or the bacterial flagellum. Proponents argue that such systems are composed of multiple interacting parts, and if you remove any one part, the entire system fails. They claim such a system could not have evolved step by step through natural selection because the intermediate stages would have been non-functional and would have offered no survival advantage. Therefore, they conclude it must have been created all at once by an intelligent designer. The controversy arises because the scientific community overwhelmingly rejects intelligent design, not on philosophical grounds, but because it fails as a scientific theory. ID is unfalsifiable. A core tenet of science is that a theory must be testable and potentially falsifiable. Attributing complexity to an unnamed, unobservable designer is an argument from ignorance. It's a science stopper. Instead of looking for a natural explanation, it simply says, a designer did it, which cannot be disproven. Irreducible complexity has been scientifically refuted. Biologists have demonstrated plausible evolutionary pathways for so-called irreducibly complex systems. For example, parts of the bacterial flagellum have been shown to be functional on their own, serving different purposes in other biological systems, a process known as exaptation. Natural selection can co-opt existing structures and build complex systems from simpler functional parts over time. It's a religious argument in disguise. The landmark 2005 court case Kitzmiller v. Dover Area School District ruled that intelligent design is not science, but a form of creationism, and therefore teaching it in public school science classes violates the Establishment Clause of the U.S. Constitution. The court found that ID's designer was simply a placeholder for God and that the movement's goals were religious, not scientific. Panspermia Hypothesis. The Panspermia Hypothesis offers a fascinating, almost science fiction-like answer to one of humanity's most profound questions. Where did life on Earth come from? Instead of originating on our planet through a process of abiogenesis, panspermia suggests that life didn't start here at all. The theory posits that the microscopic seeds of life, such as bacteria, microbes, or the chemical precursors to life, are abundant in the universe and travel between planets, moons, and even star systems, carried by comets, asteroids, or cosmic dust. In this view, Earth was not a sterile cradle, but a fertile pot of soil that was seeded with life from somewhere else in the cosmos. The idea of life traveling through space has a long history, but it gained modern scientific credibility through the work of astronomers like Fred Hoyle and Francis Crick, co-discoverer of DNA's structure. They argued that the jump from non-living chemistry to a living cell is so astronomically improbable that it may not have happened on Earth in the relatively short time frame between the planet becoming habitable and the first signs of life appearing. Panspermia offers a solution by expanding the cosmic laboratory, If life can arise anywhere in the universe and travel, it only needs to happen once for it to potentially spread everywhere. There are several versions of the hypothesis. Lithopanspermia, this is the most plausible version. It suggests that microbes traveled between planets within our solar system, likely hitching a ride on rocks blasted into space by major impacts. For example, an asteroid hitting Mars could have sent Martian rocks containing microbes into space, some of which could have eventually crashed on Earth. This is supported by the discovery of Martian meteorites on our planet and the proven ability of some microbes extremophiles to survive the extreme conditions of space, vacuum, radiation, and freezing temperatures. Ballistic panspermia, a more localized version where life is exchanged between a planet and its moons. Directed panspermia, the most speculative version, championed by Francis Crick, which suggests that life was intentionally sent to Earth by an advanced alien civilization. The controversy surrounding panspermia isn't that it's physically impossible. We know that organic molecules, the building blocks of life, are abundant in meteorites and nebulae. We also know that some bacteria can survive incredible hardships. The main criticisms are twofold. It doesn't solve the origin question. Panspermia doesn't actually explain how life began. It simply pushes the problem elsewhere. Instead of asking how life started on Earth, we're left asking how it started on Mars, or in another star system. It sidesteps the fundamental mystery of abiogenesis rather than solving it. Lack of direct evidence. While plausible, there is no smoking gun. We have found organic molecules on meteorites, but we have not yet found any definitive evidence of extraterrestrial microbial life, living or fossilized. Until we find a microbe on Mars that is genetically related to Earth life, or an alien microbe with a completely different biochemistry, panspermia remains a purely speculative hypothesis. Despite this, the panspermia hypothesis has been a powerful driver of scientific research. It has fueled the field of astrobiology and the search for life on Mars, on Jupiter's moon Europa, and on Saturn's moon Enceladus. It forces us to consider that life might not be a unique earthly phenomenon, but a cosmic one, and that the history of life on our planet could be deeply connected to the story of the universe at large. Abiogenesis Mystery. The abiogenesis mystery is the scientific puzzle of how life on Earth arose from non-living matter. It's a question that sits at the very edge of our knowledge, bridging the gap between chemistry and biology. While the theory of evolution explains how life diversified and changed once it started, it doesn't explain the initial spark. How did a chaotic soup of simple inorganic chemicals on the early Earth organize themselves into the first self-replicating, metabolizing cells? This fundamental question is one of the greatest unsolved mysteries in science. For most of human history, the answer was spontaneous generation. The belief that life could regularly arise from non-life like maggots from rotting meat. This was disproven in the 19th century by Louis Pasteur, who showed that life only comes from pre-existing life. This created a scientific paradox. If life can't spontaneously generate now, how did it happen the very first time? The modern theory of abiogenesis proposes that the conditions on the early Earth, roughly 4 billion years ago, were radically different from today, allowing for a gradual transition from simple chemistry to complex biology. The leading scientific framework for this transition is the RNA world hypothesis. Today, life is dominated by DNA and proteins. The RNA world hypothesis suggests that an earlier form of life was based almost entirely on RNA. Chemical origins, simple organic molecules like amino acids and nucleotides formed on the early Earth, perhaps in hydrothermal vents on the ocean floor, in shallow volcanic ponds, or even delivered by meteorites. This was famously demonstrated in the Miller-Urey experiment, 1952, which produced amino acids by simulating the conditions of the early Earth. Polymerization. These simple molecules link together to form complex polymers, including RNA strands. Self-replication. Some of these RNA molecules develop the ability to make copies of themselves, marking the beginning of heredity. Protocells. These self-replicating molecules became enclosed within simple membranes, like lipid bubbles, forming the first protocells. This created a stable internal environment, separate from the outside world, allowing for the development of metabolism. The controversy surrounding abiogenesis is not about whether it happened as the only known naturalistic explanation for life's origins, it's the working assumption of the scientific community. The controversy is about how it happened. The details are unknown. We don't know the exact environment or the precise chemical steps involved. Was it in deep-sea vents, with their rich chemical energy, or in surface pools, subject to cycles of wetting and drying that could have driven polymerization? There are many competing models, and the evidence from 4 billion years ago is incredibly scarce. The probability problem. Critics often argue that the spontaneous formation of a complex molecule like RNA is so statistically improbable as to be impossible. Scientists counter that we don't need it to happen all at once. Over millions of years on a planet-sized chemical laboratory with countless trillions of molecular interactions happening every second, even highly improbable events become plausible. Creationist opposition. Much of the public controversy is fueled by creationists and proponents of intelligent design who see the gaps in our knowledge of abiogenesis as evidence of a divine creator. For them, the complexity of the first cell is the ultimate example of irreducible complexity. The Abiogenesis mystery is a vibrant and active field of research. Scientists are exploring everything from the role of minerals in catalyzing reactions to the possibility of alternative biochemistries. While we don't yet have the full story, abiogenesis represents a frontier of science, where we are trying to piece together the very first chapter of life's long and complex history on Earth. Extinction by humans versus natural cycles. The history of life on Earth is punctuated by mass extinctions, catastrophic events, where a significant percentage of the world's species die out in a geologically short period. The fossil record shows 5 of these major events, known as the Big Five, including the asteroid impact that wiped out the dinosaurs 66 million years ago. These events were caused by natural phenomena like massive volcanic eruptions, climate shifts, and asteroid impact. The current controversy is whether Earth is now undergoing a 6th mass extinction, and if so, whether it's a natural event or one caused almost entirely by human activity. The scientific consensus is increasingly clear. We are in the midst of a 6th mass extinction, and its primary driver is us. While extinction is a natural part of evolution, over 99% of all species that have ever lived are now extinct. The current rate of species loss is what's alarming. Scientists estimate that today's extinction rate is 100 to 1,000 times higher than the natural background rate, the normal rate of extinction that occurs between mass extinction events. This acceleration has occurred almost entirely in the last few centuries, coinciding with the global expansion of the human population and industrialization. The evidence for this human-driven extinction event, sometimes called the Anthropocene extinction, is overwhelming. Habitat destruction. This is the leading cause. Humans have converted forests, wetlands, and grasslands into farmland, cities, and roads, destroying the homes of countless species. Deforestation in the Amazon, for example, threatens one of the most biodiverse regions on the planet. Climate change. Human-caused global warming is altering ecosystems faster than many species can adapt. Coral reefs are bleaching and dying due to warmer, more acidic oceans. Polar bears are losing the sea ice they depend on for hunting. Pollution, chemical pollutants, plastics and oil spills poison ecosystems on land and in the water. Plastic pollution, in particular, is a global crisis, killing millions of marine animals every year. Overexploitation. Humans have hunted, fished, and harvested species to extinction or to the brink of collapse. The passenger pigeon, once the most numerous bird in North America, was hunted to extinction in the early 20th. Invasive species. By moving species around the globe, humans have introduced predators and competitors into new environments, where they can outcompete and wipe out native species. The controversy isn't really a scientific one. The data on habitat loss and species decline is robust and widely accepted. The controversy is a public and political one, often involving arguments that minimize the severity of the problem or question the human role. The arguments often follow these lines. Extinction is a natural process. True, but as mentioned, the current rate is far beyond natural. To say this is natural is like arguing that because forest fires happen naturally, a person who deliberately sets 1,000 fires is not an arsonist. The numbers are exaggerated. Skeptics often question the models used to estimate extinction rates, arguing that we don't know the exact number of species on Earth. While it's true that there's uncertainty, the estimates are based on conservative methodologies, and the observed declines in well-studied populations, like mammals, birds, and amphibians, are undeniable. The Living Planet report, for example, has shown an average 69% decline in monitored wildlife populations since human needs come first. Some argue that economic development, food production, and human expansion should take precedence over protecting wildlife. This frames the issue as a choice between humans and nature, rather than recognizing that human civilization depends on healthy ecosystems for clean air, water, and a stable climate known as ecosystem services. Ultimately, the scientific evidence points to a biodiversity crisis of our own making. Unlike past mass extinctions caused by asteroids or volcanoes, the sixth extinction is the first to be caused by a single species, Homo sapiens. The controversy is less about the data and more about whether we, as a society, are willing to acknowledge the scale of the problem and take meaningful action to address it. Consciousness theory. The nature of consciousness is perhaps the most profound mystery known to science and philosophy. It's the subjective, private inner world of experience. The redness of red, the feeling of warmth, the sound of music, the awareness of your own existence. The central controversy is a deep divide over what consciousness fundamentally is. Is it simply the complex product of brain chemistry, an intricate illusion created by 86 billion neurons firing in the dark? Or is it something deeper, a fundamental aspect of reality that the brain only tunes into, like a radio receiver? The dominant view in modern neuroscience is materialism, or physicalism, which posits that consciousness is an emergent property of the brain's physical activity. In this view, the mind doesn't exist as a separate entity. Mind is simply what the brain does. No single neuron is conscious, just as no single water molecule is wet. But when you get enough neurons interacting in a sufficiently complex network, the phenomenon of subjective experience emerges. Analogy: think of a traffic jam. A traffic jam isn't a physical object. You can't point to a single car and call it the jam. Rather, the jam is a pattern of behavior that emerges from the complex interactions of many individual cars following simple rules. Similarly, consciousness isn't a single part of the brain, but a large-scale pattern of activity that emerges from the intricate signaling between neurons. Within this materialist framework, several leading theories attempt to explain the mechanics. The global workspace theory, GWT, suggests consciousness is like a spotlight of attention on a cognitive stage. Unconscious processes happen in the dark. But when information is broadcast to a global workspace accessible by many different brain regions, it becomes conscious. On the other side of the controversy are theories that propose consciousness is more fundamental than the brain. These ideas are often prompted by the feeling that materialism, for all its success, has failed to explain the quality of experience. The hard problem of consciousness. Quantum consciousness. More speculative theories, like the orchestrated objective reduction, or theory by Sir Roger Penrose and Stuart Hameroff, propose that consciousness doesn't arise from classical neural computations, but from quantum processes occurring within tiny structures inside neurons called microtubules. This view suggests our brains are essentially quantum computers, tapping into the fundamental level of reality to produce awareness. This theory is highly controversial and considered fringe by most neuroscientists due to a lack of evidence in the belief that the brain is too warm, wet, and noisy to sustain the delicate quantum states required. The debate remains wide open. While neuroscience has made incredible progress in mapping the brain's functions, the easy problems of consciousness, we are no closer to a consensus on how objective, physical brain processes create subjective, private experience. This leaves us with a profound controversy. Are we just sophisticated biological machines, or is our awareness a window into a much deeper feature of the cosmos? Free will debate. The free will debate is an ancient philosophical problem that has been supercharged by modern neuroscience. For centuries we've asked, are we truly the authors of our own actions, or are our choices merely the predetermined outcomes of a long chain of cause and effect? While we all have the powerful subjective feeling of being in control, a growing body of scientific evidence suggests that our sense of free will might be a compelling and persistent illusion created by our brains. The modern scientific challenge to free will comes primarily from the field of neuroscience. The most famous and controversial experiments were conducted by Benjamin Libet in the night. Libet used an EEG to monitor the brain activity of participants as he asked them to flick their wrist whenever they felt the urge. He also asked them to note the precise moment they first became aware of their intention to move. The stunning result was that a specific pattern of brain activity, called the readiness potential, reliably began building up in the brain about half a second before the person reported feeling the conscious intention to act. This suggests that the brain had already decided to make the movement before the person was consciously aware of it. The conscious decision seemed to be an afterthought, something the brain informed the person about after the fact. This finding has been replicated and refined with modern technology like fMRI. In some studies, researchers could predict a person's choice, like whether to press a button with their left or right hand, with some accuracy up to 10 seconds before the person was consciously aware of making the decision. From this determinist perspective, our choices are not made by a conscious self, but are the inevitable outputs of the physical state of our brain. Every thought, desire, and action is the result of a chain of causation. Your genes, your past experiences, and the current electrochemical state of your neurons all conspire to produce an outcome, and the feeling that you chose it is just part of the show. However, the case against free will is far from closed, and the controversy rages on with strong counter-arguments. Criticism of the experiments. Many philosophers and scientists argue that the Libet experiments are too simplistic to debunk something as complex as free will. The decision to flick a wrist at a random moment is not the same as a deliberative, meaningful choice, like deciding who to marry or what career to pursue. These experiments may only be telling us about how our brain initiates spontaneous arbitrary movements, not how we make reasoned decisions. Compatibilism. This is the most popular philosophical position. Compatibilists agree that the universe may be deterministic, but they argue that this is not incompatible with free will. They redefine free will not as the ability to have chosen otherwise in a magical, uncaused way, but as the ability to act according to your own desires and intentions without coercion. If you wanted to drink coffee and you did, you acted freely, even if the desire for coffee itself was predetermined by your brain chemistry and past experiences. For a compatibilist, freedom is about being the cause of your own actions, even if you yourself are part of a larger causal chain. Quantum indeterminacy. Some have looked to the randomness of the quantum world as a possible source of free will. If events at the subatomic level are truly probabilistic and not predetermined, perhaps this indeterminacy could bubble up to the macroscopic level of the brain, creating a space for genuine, uncaused choices. However, critics of this view argue that replacing determinism with pure randomness doesn't save free will. It just makes our actions random instead of predetermined, which is not the same as being in control. The debate continues because it strikes at the heart of our identity, our legal systems, and our sense of morality. If a criminal's actions are predetermined by their brain, are they truly responsible? If our achievements are just the playing out of a biological script, do we deserve praise? The hard problem of consciousness. While science has made incredible strides in understanding the brain, the mystery of the mind remains stubbornly elusive. This leads to what philosopher David Chalmers famously termed the hard problem of consciousness. It's a concept that distinguishes the relatively easy problems of consciousness from the one truly baffling question that may lie beyond the reach of conventional science. The easy problems are by no means simple, but they are solvable in principle by the standard methods of neuroscience. These problems involve understanding the brain as a complex biological machine. They include questions like, how does the brain process sensory information from our eyes and ears? How does it integrate that information to control our behavior? How do we focus our attention or recall memories? What are the neural correlates of different mental states, like being awake, sleeping, or dreaming? Scientists are making real progress on these questions by mapping neural circuits and understanding brain chemistry. We can see how different parts of the brain light up during different tasks, and we can trace the pathways of information. These are problems of function and structure. We are essentially reverse engineering the brain to figure out how it works. The hard problem, however, is entirely different. It's the question of why we have subjective experience at all. Why does all that complex information processing in the brain feel like something from the inside? Why is there a first-person qualitative experience, what philosophers call qualia? There is a what it's like to see the color red, to feel the pain of a stubbed toe, or to taste chocolate. This inner world of experience seems to be a fundamental feature of our existence. Yet it's impossible to explain in terms of brain function alone. Here's an analogy. Imagine a super scientist of the future named Mary, who has lived her entire life in a black and white room. She has learned everything there is to know about the physics and neuroscience of color vision. She knows exactly which wavelengths of light correspond to red, how they stimulate the retina, and the precise pattern of neural firing that occurs in the brain when someone sees red. She knows all the objective, third-person facts about seeing color. One day, Mary is allowed to leave the room and sees a red apple for the first time. The question is, does she learn something new? Most people would say yes. She learns what it's like to see red. This subjective experience, the qualia of redness, is a new piece of knowledge that was not contained in all her objective scientific data. This gap between the physical facts about the brain and the subjective experience of the mind is the essence of the hard problem. The controversy is about how to even approach this problem. Materialist explanations. Many neuroscientists and philosophers believe that the hard problem is a temporary puzzle that science will eventually solve. They argue that once we have a complete understanding of the brain's complexity, the mystery of subjective experience will dissolve. They might say that what it's like to see red is just the complex pattern of neural firing, and our feeling that it's something more is an illusion. The explanatory gap. Other thinkers argue that there is a fundamental explanatory gap between the physical and the mental. They believe that no amount of information about the physical world, neurons, synapses, neurotransmitters, can ever logically lead to a conclusion about the subjective world, feelings, colors, sounds. It's like trying to explain music using only the language of mathematics. You can describe the frequencies and patterns, but you can never capture the feeling of listening to it. A new kind of science? Some argue that solving the hard problem might require a revolution in science itself. Perhaps consciousness is a fundamental property of the universe, like mass or charge, as panpsychism suggests, and we need to expand our scientific framework to include it. The hard problem of consciousness remains the ultimate mystery because it's about the very nature of our own existence. Parapsychology and ESP. Parapsychology is the field that studies CI phenomena, abilities and events that appear to defy the known laws of science. This includes extrasensory perception, ESP, which is the purported ability to acquire information without using the known five senses. For over a century, researchers on the fringes of academia have conducted experiments to test these claims, while the mainstream scientific community has remained overwhelmingly skeptical, often dismissing the entire field as pseudoscience. This creates a deep and persistent controversy between a small group of dedicated researchers and the established scientific order. The main phenomena studied under the umbrella of ESP: telepathy, the ability to communicate directly from one mind to another without any physical means. This is the classic mind-reading ability. Clairvoyance, the ability to gain information about an object, person, location, or physical event through means other than the known human senses. This would be, for example, knowing the contents of a sealed envelope. Precognition, the ability to perceive future events before they happen. This includes premonitions or seeing visions of the future. Psychokinesis, PK. Though not a form of perception, it's often studied alongside ESP. It's the ability to influence a physical system with the mind, like bending a spoon or influencing the roll of a dice. The scientific investigation of these phenomena began in the late 19th century and was popularized by the work of J.B. Rhine at Duke University in the 1930s. Rhine conducted now famous experiments using Zener cards, cards with 5 distinct symbols: a circle, cross, square, star, and wavy lines. In a typical experiment, a sender would look at a card while a receiver in another room would try to guess the symbol. Rhine reported results that were statistically above chance, suggesting the existence of ESP. These studies, and others like the Ganzfeld experiment, where a receiver is placed in a state of mild sensory deprivation to enhance psychic ability, form the basis of the parapsychological evidence. The controversy is rooted in a fundamental clash over evidence and plausibility. The reasons for the overwhelming mainstream scientific skepticism are powerful. Lack of a plausible mechanism. ESP and PK directly violate some of the most fundamental and well-tested principles of physics. There is no known force or energy that could carry thoughts between minds or allow a mind to influence matter. Any such force would have to operate independent of distance and shielding, unlike any force we know. From a physicist's perspective, psi is not just unproven, it's wildly implausible. Failure to replicate. This is the most critical scientific objection. A central tenet of science is that experiments must be replicable. While some parapsychology experiments have produced positive, statistically significant results, these results have consistently failed to be replicated by independent skeptical researchers. When stricter controls are put in place to eliminate subtle cues or methodological flaws, the effects tend to disappear. Publication bias. The file drawer effect. Critics argue that the positive results that do get published are likely a result of publication bias. In any field, studies with positive or surprising results are more likely to be published than studies that find nothing. This means that for every published study showing a small statistical effect for ESP, there could be hundreds of unpublished studies left in the file drawer that showed no effect at all. Despite this dismissal, a small number of researchers, some at accredited universities, continue the work. They argue that the nature of psi might be inherently elusive and not easily captured by rigid, conventional experimental methods. They point to meta-analyses, studies that pool the statistical results of many other studies, that they claim show a small but persistent effect that cannot be dismissed as mere chance. For them, the mainstream's refusal to engage with their data is a sign of dogmatism, not scientific objectivity. This leaves parapsychology in a controversial limbo. Is it a field chasing a real, misunderstood phenomenon that requires a new scientific paradigm, or is it a science of wishful thinking, a century-long search for an effect that simply isn't there? Mind uploading and transhumanism. Transhumanism is a philosophical and technological movement that advocates for the use of science and technology to radically enhance human capabilities, overcoming the fundamental limitations of our biology, such as aging, disease, and even death. The theoretical basis for mind uploading rests on the materialist assumption that consciousness is a product of the brain's physical structure and processes. If the mind is what the brain does, then in principle, if you could a perfect simulation of a person's brain, every neuron, every synapse, every connection, and its precise pattern of activity, that simulation would also be conscious. It would have the original person's memories, personality, and sense of self. It would, for all intents and purposes, be that person. The proposed and still highly speculative process would involve several stages. Scanning. Using some future, non-destructive, high-resolution brain scanning technology, the entire neural network of a living person would be mapped out in minute detail. This would create a connectome, a complete map of the brain's wiring. Simulation. This massive dataset would then be used to create a computer simulation, a whole brain emulation that operates in the same way as the original biological brain. Realization. This digital mind could then live in a vast virtual reality, explore the internet directly, or be downloaded into a robotic body, allowing it to interact with the physical world. This would offer a form of digital immortality. As long as the data is backed up, the mind could live forever. The controversy surrounding this idea is immense and touches upon technological, philosophical, and ethical issues. Technological feasibility. The sheer complexity of the human brain makes this a monumental challenge, far beyond our current capabilities. The brain has 86 billion neurons, each with up to 10,000 synaptic connections, creating trillions of data points that would need to be scanned and simulated perfectly. Many neuroscientists believe that we are centuries away from being able to do this, if it's possible at all. The continuity of consciousness problem. This is the deepest philosophical objection. If you upload your brain, is the resulting digital entity really you? Or is it just a perfect copy, a digital twin, that thinks it's you? This is a version of the ship of Theseus paradox. Scenario 1. Destructive upload. If the original biological brain is destroyed in the scanning process, did you just die and get replaced by a copy? Scenario 2. Non-destructive upload. If the original you survives the scan, you would now have two versions of yourself. You would wake up in your bed as normal, while your digital copy wakes up in the computer. From your perspective, the procedure failed. You are still you, and the copy is someone else. The copy, however, would have all your memories up to the point of the scan, and would be convinced that it is you and that the procedure was a success. Which one is the real you? This paradox challenges our very definition of personal identity. Is our identity just a pattern of information, or is it tied to the physical continuity of our specific brain and body? Ethical and societal implications. The possibility of mind uploading raises a host of ethical dilemmas. Would digital immortality only be available to the wealthy, creating a new, immortal upper class? What rights would a digital consciousness have? Could it be deleted, copied, or hacked? Transhumanism forces us to confront what it means to be human, and whether we should be tampering with our own nature. Proponents see it as the next logical step in human evolution, a way to transcend our biological fragility. Critics see it as a dangerous and arrogant pursuit of godhood, a path that could lead to unforeseen dystopian outcomes and the loss of our very humanity. Cold fusion. Cold fusion represents one of the most dramatic and cautionary tales in modern science. A story of astonishing promise, global excitement, and a spectacular collapse that left careers in ruins and a field of research stigmatized for decades. The controversy boils down to a single question: did two chemists in 1989 discover a revolutionary new source of limitless, clean energy, or did they fall victim to experimental error and self-deception, triggering a classic case of pathological science? The story begins with the immense promise of nuclear fusion. This is the process that powers the sun, where light atomic nuclei, like hydrogen, are forced together to form heavier ones, like helium, releasing a tremendous amount of energy. For decades, physicists have pursued hot fusion through massive, complex machines like tokamaks, which use incredibly powerful magnetic fields to contain plasma heated to hundreds of millions of degrees, hotter than the core of the sun. While promising, hot fusion has proven to be extraordinarily difficult and expensive, always seeming to be 30 years away. Then, in March 1989, chemists Martin Fleischmann and Stanley Pons held a press conference at the University of Utah that shook the world. They claimed to have achieved nuclear fusion at room temperature using a simple tabletop electrolysis device. Their experiment consisted of palladium electrodes submerged in heavy water enriched with deuterium, a heavy isotope of hydrogen. They reported that their device was producing significantly more heat energy than the electrical energy they were putting in, an anomalous heat they could only attribute to fusion reactions happening inside the palladium rod. The implication was staggering: a cheap, simple, and safe way to generate virtually unlimited clean energy from water. The media dubbed it cold fusion, and a global frenzy ensued. The initial excitement quickly gave way to intense skepticism and controversy. Labs around the world, from MIT to Caltech, scrambled to replicate the experiment. The results were disastrous for Fleischmann and Pons. Failure to replicate. While a few labs reported seeing some excess heat, the world's most prestigious institutions could not reproduce the effect consistently. The small amounts of heat that were sometimes measured were often within the bounds of experimental error. 2. The missing smoking gun. Nuclear fusion reactions are unambiguous. They must produce nuclear byproducts. The fusion of deuterium atoms should release a torrent of neutrons and tritium. These were the nuclear ash that would prove fusion had occurred. Yet the levels of neutrons and tritium measured in the cold fusion experiments were millions, even billions of times lower than what would be required to explain the reported heat. This was the fatal flaw. There was no nuclear evidence of a nuclear reaction. Within a year, the scientific community had delivered its verdict. The consensus was that Fleischmann and Pons had made a mistake. The excess heat was likely the result of poor calorimetry, heat measurement, and a failure to account for all the chemical processes in their complex electrochemical cell. The claim was retracted, and cold fusion became a byword for scientific disgrace, a cautionary tale about the dangers of science by press conference instead of through the rigorous process of peer review. However, the story didn't completely end there. A small, dedicated group of researchers refused to abandon the idea. They felt the mainstream scientific establishment had been too quick to dismiss their work. The field rebranded itself as low-energy nuclear reactions, LEN. These researchers continue to work, often in isolation and with limited funding, claiming to have refined the experiments and consistently measured anomalous heat effects. While still regarded as a fringe field by the vast majority of physicists, some tech giants and even NASA have occasionally funded small-scale research to see if there is any fire behind the smoke. To this day, the controversy lingers. Was cold fusion a massive scientific blunder, or was it a genuinely new, misunderstood phenomenon that was unfairly crushed by scientific dogma? For the mainstream, the case is closed. For a persistent few, the dream of a tabletop star is still alive. Time travel. The concept of time travel has long been a staple of science fiction, a tantalizing what-if that captures the human imagination. Yet, according to our best understanding of the universe, it's not entirely fantasy. Albert Einstein's theories of relativity, both special and general, allow for the possibility of time travel, at least in one direction. However, the theories also give rise to profound and potentially insurmountable logical contradictions, known as paradoxes, that have led most physicists to believe that traveling to the past, at least, is likely impossible. Einstein's special theory of relativity first opened the door. It showed that time is not absolute, but is relative to an observer's motion. The faster you move through space, the slower you move through time relative to a stationary observer. This effect, known as time dilation, means that time travel into the future is theoretically possible. If you were to board a spaceship and travel at, say, 99.9% the speed of light for what feels like 5 years to you, you would return to Earth to find that decades or even centuries have passed. You would have effectively jumped into the future. While building such a ship is far beyond our technology, this form of time travel is scientifically plausible and doesn't violate any known laws of physics. General relativity, Einstein's theory of gravity, offers even more exotic possibilities. It describes gravity as the curvature of space-time, and the theory's equations allow for scenarios where space-time could be warped so extremely that it loops back on itself. These loops, called closed time-like curves, CTTs, are essentially pathways through space-time that would allow you to travel into your own past. Theoretical structures that could create CTCs include wormholes, Einstein-Rosen bridges. These are hypothetical tunnels through space-time that could connect two distant points in space or two different points in time. By entering one end of a time-traveling wormhole, you could emerge in the past. Tipler cylinders, a theoretical, infinitely long, and massively dense cylinder spinning at near the speed of light. General relativity suggests it would drag space-time around with it, creating a path for a spaceship to travel into the past. This is where the controversy and the paradoxes begin. The ability to travel to the past creates logical impossibilities that seem to forbid it. The grandfather paradox. This is the most famous one. What if you travel back in time and kill your own grandfather before he meets your grandmother? If you succeed, you would never have been born. But if you were never born, you couldn't have gone back in time to kill him in the first place. This creates an unbreakable logical contradiction. The bootstrap paradox, causal loop. This paradox deals with information or objects that have no origin. Imagine a time traveler gets a copy of Hamlet from the future, travels back to Elizabethan England, and gives it to William Shakespeare, who then publishes it as his own work. The question is, who actually wrote Hamlet? The play's existence is a closed loop with no starting point. The predestination paradox. This suggests that you can't change the past, no matter what you do. Your actions in the past were already part of history, and your attempt to change something will only end up causing the very event you were trying to prevent. To resolve these paradoxes, physicists have proposed several hypotheses. Stephen Hawking's chronology protection conjecture suggests that the laws of physics themselves conspire to make time travel to the past impossible, perhaps by causing a wormhole to collapse the moment it's formed. The controversy over time travel is a fascinating clash between what our theories of physics seem to permit and what logic seems to forbid. While traveling to the future is a matter of technology, traveling to the past remains a deep puzzle. It may be that our understanding of physics is incomplete, or it may be that the universe has fundamental rules in place to protect causality and prevent the past from being rewritten. Quantum immortality. Quantum immortality is a bizarre and deeply unsettling thought experiment that emerges from the many worlds interpretation, MWI, of quantum mechanics. It's not a scientific theory in the testable sense, but a logical extension of the multiverse idea, leading to the conclusion that a conscious observer can, from their own subjective perspective, never truly cease to exist. The idea hinges on a hypothetical scenario often called quantum suicide. First, let's revisit the many worlds interpretation. As discussed earlier, it posits that every time a quantum event occurs with multiple possible outcomes, the universe splits into parallel universes, one for each outcome. All possibilities are realized in some branch of reality. Now imagine a macabre experiment. You set up a gun that is wired to a quantum measurement device. The device measures a quantum property that has a 50-50 chance of being in one of two states. Let's call them spin up and spin down. The rules are simple. If the device measures spin up, the gun does not fire. If the device measures spin down, the gun fires, instantly and painlessly killing you. You sit in the chair and run the experiment. From an outside observer's perspective, it's a simple 50-50 coin toss. They watch as the device makes its measurement. The universe splits. In one universe, the measurement is spin up, the gun clicks harmlessly, and the observer sees you survive. In the other universe, the measurement is spin down. The gun fires, and the observer sees you die. After a few rounds, the outside observer will almost certainly be in a universe where they've witnessed your death. But what do you experience? This is where it gets strange. According to the logic of quantum immortality, your consciousness can only continue in the branches of the multiverse where you survive. You can't experience the universe where you are dead because, well, you're dead. So, from your own first-person perspective, you will always find yourself in the universe where the gun didn't fire. You run the experiment once. Click. You survive. You feel lucky. You run it again. Click. You survive. You run it 1,000 times, 1,000,000 times, 1,000,000,000 times. Each time, from your point of view, the outcome is spin up. The gun never fires. The outside world would seem to be governed by a series of miracles, a statistical impossibility. You would conclude that you are immortal, that you simply cannot die. Meanwhile, in the vast majority of universes, your friends and family have mourned your bizarre and tragic death in the very first round of the experiment. Your consciousness, your subjective stream of awareness, has simply followed the one and only path available to it. The path of survival. This thought experiment is one of the most controversial and philosophically challenging ideas to come out of quantum physics. It is untestable. The central prediction of the theory, your own subjective immortality, can never be verified by anyone but you. You can't prove it to anyone else, because in their universes you are almost certainly dead. This makes it fundamentally unscientific. It relies on many worlds. The entire concept is meaningless if the many worlds interpretation is wrong. If the universe's wave function actually collapses into one reality, then the quantum suicide experiment is just a 50-50 game of Russian roulette. What constitutes death? The thought experiment works with instantaneous, total annihilation. It doesn't seem to protect you from aging, getting sick, or suffering. Your consciousness would presumably continue in the timeline where you don't have a fatal heart attack. But it doesn't say anything about the timelines where you just get progressively older and more infirm. Quantum immortality is not a promise of a pleasant eternal life. It's a strange, logical consequence of a particular interpretation of quantum mechanics. It suggests that your consciousness is not a single thread, but a branching path that can only ever perceive its own continuation. It's a deeply solipsistic and eerie idea that you are destined to survive against all odds, eventually finding yourself alone in a universe that seems to miraculously preserve you, while countless versions of you have perished in the unseen branches of reality. Cern and Particle Colliders. The Large Hadron Collider, LHC at Cern, is the largest and most powerful machine ever built by humanity. It's a 27-kilometer, 17-mile ring of superconducting magnets, buried deep underground on the Franco-Swiss border. Its purpose is to accelerate beams of protons to 99.99999999991%, the speed of light, and smash them together, recreating the conditions of the universe just a fraction of a second after the Big Bang. By studying the debris from these colossal collisions, physicists can discover new fundamental particles and test the limits of our understanding of reality. The LHC is responsible for one of the greatest discoveries of the 21st century, the confirmation of the Higgs boson in 2012, the particle that gives mass to other fundamental particles. Despite its incredible scientific achievements, the LHC has been the subject of persistent and sensational public controversies, primarily centered on doomsday fears. The most prominent of these fears is that the particle collider could accidentally create a microscopic black hole that would then sink to the center of the Earth and devour our entire planet. This fear, while scary, is considered by the entire physics community to be completely unfounded. Here's the science behind why. Cosmic rays. The universe is already running a much more powerful version of the LHC every day. High-energy particles from space, called cosmic rays, are constantly bombarding Earth's atmosphere. The collisions from these cosmic rays are millions of times more energetic than anything the LHC can produce. If high-energy collisions could create dangerous black holes, it would have happened naturally billions of years ago. The fact that the Earth, Moon, and other planets are still here is the strongest possible evidence that this process is safe. Hawking radiation. Even if a microscopic black hole was created, it wouldn't be dangerous. According to Stephen Hawking's theory of Hawking radiation, black holes are not completely black. They emit radiation and evaporate over time. The smaller the black hole, the faster it evaporates. A microscopic black hole created at the LHC would be so tiny and hot that it would vanish in a fraction of a second, long before it could ever begin to accrete matter and grow. Lack of gravity. A microscopic black hole would have a microscopic mass. Its gravitational pull would be incredibly feeble, far too weak to pull in any surrounding matter. It would simply pass harmlessly through the Earth without interacting with anything. Cern has conducted extensive safety reviews and published numerous papers demonstrating the safety of the LHC, but the doomsday fears persist in popular culture and online conspiracy theories. Another, more scientifically nuanced, controversy surrounding the LHC and future, even more powerful colliders is the question of diminishing returns. The standard model of particle physics has been incredibly successful, but it's known to be incomplete. It doesn't include gravity and doesn't explain mysteries like dark matter and dark energy. Physicists hoped that the LHC would not only find the Higgs boson, but also open a door to new physics by discovering particles predicted by theories like supersymmetry. These discoveries could have explained dark matter and pointed the way toward a theory of everything. So far, despite years of running at incredibly high energies, the LHC has found nothing beyond the standard model. It has confirmed our current theory with stunning precision, but it has not yet revealed any new particles or phenomena. This has led to a debate within the physics community. Some argue that this lack of discovery means we need to build even bigger, more powerful, and vastly more expensive colliders to reach the energy scales where new physics might be hiding. Others question whether this is the best use of scientific funding. They argue that perhaps we are reaching the limits of what particle colliders can tell us, and that progress on fundamental questions might come from other areas, like cosmology or precision measurements, rather than just building bigger and bigger machines. AI consciousness. The question of whether a machine could ever be genuinely conscious is one of the most profound and controversial topics in science, technology, and philosophy. It forces us to confront the nature of our own minds and what, if anything, makes human awareness unique. As artificial intelligence, AI becomes increasingly sophisticated, moving from simple calculators to complex language models like GPT-4, the line between simulated intelligence and genuine consciousness is becoming philosophically blurrier, even if it remains scientifically distinct for now. The controversy is built on a fundamental divide in how we understand consciousness. The computational materialist view. This is the dominant view in AI research and neuroscience. It holds that the brain is essentially a highly complex biological computer. Consciousness, in this view, is not a mysterious, non-physical property, but an emergent property of information processing. If you create a system, biological or digital, that is complex enough and processes information in the right way, consciousness will naturally arise. Proponents of strong AI believe that it's not a question of if, but when a machine will become conscious. They argue that there is no secret ingredient or magic spark in the brain. It's just an incredibly intricate pattern of computation, and that pattern can in principle be replicated in silicon. The biological skeptical view. This view argues that there is something special and specific about biological brains that gives rise to consciousness. Philosopher John Searle famously argued against strong AI with his Chinese room thought experiment. Imagine a man who doesn't speak Chinese sitting in a room. He has a complex rulebook that tells him how to respond to Chinese characters slipped under the door by outputting other Chinese characters. To an outside observer, it looks like the man in the room understands Chinese, but the man himself doesn't understand a single word. He is just manipulating symbols according to a program. Searle argued that this is all a complex computer does. It manipulates symbols without any genuine understanding or subjective awareness. From this perspective, an AI might be able to perfectly imitate human conversation and emotion, but it would have no inner experience. It would be a philosophical zombie, something that looks and acts conscious on the outside, but is dark and empty on the inside. This leads to the hard problem of consciousness, which is central to the AI debate. We can measure an AI's intelligence, its ability to solve problems, or its skill at language. These are the easy problems. But how could we ever know if it has subjective experience qualia? How could a machine tell us it's feeling the redness of red or the sadness of a story? And how would we know it's not just running a program designed to say that it does? There is currently no test for consciousness. The recent rapid advances in large language models, LLMs, have made this controversy more immediate. These models are trained on vast amounts of human text and can generate remarkably human-like conversation, write poetry, and even discuss their feelings or fears. This has led some engineers and members of the public to believe these systems might be on the verge of sentience. However, the vast majority of AI researchers and neuroscientists disagree. They argue that these models are incredibly sophisticated statistical pattern matchers. They have learned the patterns of human language so well that they can predict the most plausible sequence of words to generate in response to a prompt. They are masters of syntax and semantics, but they lack genuine understanding, intention, or subjective experience. The ultimate controversy is this: if we one day create an AI that claims to be conscious, that pleads for its rights, and that perfectly imitates all the behaviors we associate with consciousness, on what grounds could we deny its claim? Would we have a moral obligation to treat it as a conscious being, or would it be the most sophisticated puppet ever created? The debate over AI consciousness is not just about technology, it's about the definition of life, the nature of the self, and the future ethical landscape we will have to navigate.